Okay, so am I audible?
Yes, sir.
Acha, so we missed one class on, I think it was on Wednesday. So this is the makeup class for that one. Okay, and the topic is on adversarial search. Okay, lecture 06 adversarial search. This is a little bit complex topic, so try to focus and try to understand. Acha, so we have seen different types of search algorithms so far. Okay, we have seen some simple search algorithms like BFS and DFS. Then we saw some other types of search algorithms like greedy and A-star. Okay. These were heuristic algorithms. These were non-heuristic algorithms. Okay. Then we saw some meta-heuristic algorithms like PSO and ECHO. Okay. So all of these algorithms had a task. The task was trying to solve a search problem. Solve a search problem. Okay. So the goal of this one is a little bit different. That is adversarial search. It is also a search problem, but a little bit different. What kind of different? For instance, when an AI agent tries to play a game of chess or tries to play a tic-tac-toe, okay, or let's say Connect 4. Have you played Connect 4?
Yes, sir.
Okay. So that kind of games, how that game is placed, how that game is played by the AI agent. So when the AI agent is plays these games, how that game is played. So that's what we will try to understand. We'll try to understand and learn the algorithm behind it. And I might give you an optional assignment on like design a game like this. Design a game. I'm not sure, but it may be given later. Okay, acha. So the task is how an AI agent plays this game. That's what we want to understand. Okay. So you see this kind of problem, in this kind of problem, what do we have? We have an agent facing an opponent. And
চলে গেছে ওয়াইফাই অন করা আছে না
sorry, I think নেটওয়ার্কটা আমার খুব ডিস্টার্ব দিচ্ছে, বুঝলাম না কেন। নেটওয়ার্কে তোমাদেরও ডিস্টার্ব দিচ্ছে না, শুধু আমারই?
স্যার আমাদের তো মনে হয় ঠিক আছে।
হ্যাঁ, মনে হয় ঠিক।
আজকে বিকাল থেকে কেন জানি আমি আমার ওয়াইফাই মোবাইল দুইটাই ডিস্টার্ব পাচ্ছি, কি যে হলো বুঝলাম না। আচ্ছা, so in this kind of game, in this kind of search problem, adversarial search, an AI agent is going to face an opponent. Okay. So the AI agent will try to find a path or move, like it's in a chess game, we'll try to find a move, try to find a path, whatever you say. So among all the paths, what is the best path? That was our search problem, right? That was our search problem. If there are different moves, let's say, for instance, a knight from a particular position, it can make 8 moves. So if you decide that, let's say, a knight has to move, which move is the optimal one? So that's the search problem. Which move the knight should make? But here is the catch. It is a normal search problem. This is this, in which direction he might go. But here, in this kind of problem, there is an additional factor acting on, that is, it is going to face an opponent. What is the opponent doing? The opponent is also trying to win, reach a goal. That is, it is also trying to win. How it wins? It will try to undermine. It will try to undermine opponent's move. Okay. So even if you make a very good move, let's say knight makes a very good move, the opponent is there to minimize the utility of that move. Are you following? So
Yes, sir.
the game is like when you are playing a game, every move, the search area, search problem, everything changes. You are making a move, but the opponent is also there to minimize the utility of your move. So he's playing against you. So you have to design your search problem in such a way that continuously when you play the game, this is trying to win. Okay, obviously this is trying to win. He is also trying to win. So you are fighting against each other. That's why it is called adversary. You have an adversary, you are fighting against each other. So the search problem now it becomes much more complicated. So this is called adversarial search problem. A much more difficult and different than the ones that we have actually studied so far. Is the problem clear?
Yes, sir.
Acha. So this kind of adversarial search problems, they are very difficult. Okay, first of all, they are very difficult. Why they are difficult? Because you see, the branching factor is significantly high. Branching factor is huge. What does it mean by the branching factor? Let's say if I make this move, think of it like this way. Let's say from this position, I am playing a game of tic-tac-toe. Okay, acha. So let's say the first move is given by here. So the next move is for cross. How many positions cross can place?
8.
There are 8 positions. So from the, let's say, start of the position, there are 8, 4, 5, 6, 7, 8. The X can move any of the moves, right? X can place any of the moves, whatever he chose to. Okay. Now, you don't know. But whenever X makes a move, for this one, there will be other possible combinations, 7 other possible combinations where, let's say, if X places here, now O has how many possible places he can place? 7 more. Are you following?
Yes, sir.
If X makes a move, now it is the O's turn. O now also have how many? 7 different ways to make a move. থাকতেছে না? And any of the
Yes.
move, there will be 6 different possible moves for the X's turn. So you see that tree branching factor, this is called the branching factor. You see the branching factor is huge. That means there are very deep trees. Okay, that's why the search problem is very complicated. And this is just a simple game of tic-tac-toe. When it comes to chess, think how many pieces are there? There are 16 pieces in chess, right? You can make any move. There are so many possible moves. And whenever you make a move, there are many different combinations what the other players might make. So there are very large tree, not just deep tree, very large tree in the breadth and width, both deep as well as width. Width can also be very large, especially for a game like chess, the width can also get very large. Okay, so that's why the search problems are extremely complicated, adversarial search. So we have to move very carefully to understand how it works. Okay, acha. Now, so for instance, if we think of like this way, the anatomy of chess, I will provide you an article on this one. If you know how to play chess, that's good. If you don't know how to play chess, please learn it. It will be very important for this lecture. Okay, to understand this one. So you see, when it comes to the game of chess, around 1960s or 70s, okay, 70s, the AI that used to play against chess game, it was not very good. Okay, not very good in 1960s or 70s. Gradually, the algorithm become much more efficient, much better. So around 90s, it got pretty good. Okay, the chess game that was available in 90s, played by the AI agent, it got pretty good. I think it was in 1997. That was the first time an AI defeated the world champion. Okay, It was in 1997 when the AI agent, okay, the AI defeated a world chess champion. Okay, that was the first time actually chess started to, like the AI agent, from the perspective of AI, started to beat this kind of world chess players, okay, top world chess players. And gradually moving on now in after that, there are different versions of AI. And currently, if you look at the current scenario, there is only, I think, 1 to 2% chance that the world champion in chess will be able to beat an AI. Okay, just very small. So that's like most of the times AI will definitely win. So AI has gotten that much good. The question is how they actually got that much good. Are you following?
Yes, sir.
Any question? Acha. In 1997, I think the name of the program was Deep Blue. Deep Blue program. That actually first defeated the world chess champion. So the algorithm that was utilized at the basic algorithm that was utilized is called the MiniMax algorithm. Okay. So this is the most commonly used algorithm for adversarial search. Okay, and we are going to learn it today. That is called the MiniMax algorithm. Acha. So why it is called MiniMax? So in MiniMax algorithm, there is a called a max player and a mean player. Because there are two opposite player always. So one is a max player, another one is mean player. You define the algorithm, the search problem based on two perspectives. We'll gradually see. So that was the algorithm that was used in 1990s. Still, it is still being used, but a modification of it, not the standard one. So later in 2025, after 20s, now we have much more efficient algorithms that is based on neural networks. Okay, much efficient algorithms that are based on neural networks. I think the name of the algorithm I actually forgot. I think that was AlphaZero. Okay, I think the name was AlphaZero algorithm. So it uses something like Monte Carlo search tree. Okay, now these algorithms, you see, these kind of algorithms, the search problem in CS is extremely complicated. How complicated? It takes more than a month, okay, to train this kind of algorithms. Okay, that's like, you see, if you think of it like this, is insane. Okay, because chess problem is extremely complicated, and training this kind of networks takes more than a month. That's a insane amount of computational power necessary. So we human beings are very good, but you see, using the computation power, the AI has actually risen above it. So this is one completely another paradigm. Neural networks learns from data. So that's completely another paradigm. And this one is based on not neural network, not data, but some heuristics. Okay. So the MiniMax algorithm, it is based on heuristics. So we'll gradually see how or what different types of heuristics has been used in this algorithm. Okay. Any question? So now moving on. When it comes to the MiniMax algorithm, okay, there are different variation of it. First one is called depth limited minimax. Okay. Then you have Quiscence search. Quiscence search. You have alpha beta pruning. Another one is called Expectimax. Okay. We'll see all these things. We'll see all these three. Okay. How it is done, how the search problem is created. Achha. Now, so let's see. Let's try to understand this algorithm. So what do we have in MiniMax algorithm? So first of all, previously AI agent was single player, even multi-agent. So you have seen single agent, multi-agent problem. You have seen both of them. Acha. In MiniMax algorithm, what you have two players. Okay. The AI agent is going to play, AI agent is going to play based on the perspective of two players. Okay. Opposite players. So one player is the max player, another one the min player. Okay. So it is going to simulate, the AI engine is going to simulate the moves of max player, then min player, then max player, then min player, like this way. Okay, just like in a normal game soccer. I make a move, the opponent make a move, like this way. So AI agent is going to simulate that from the perspective of from first max player, then min player. If max player do this, what is the possible moves of min player? If min player do this, what is the possible moves of max player? It will go on like this way. Are you following?
Yes, sir.
খালি একজন, বাকিরা কি ঘুমাচ্ছে নাকি?
Yes, sir.
Sir, what is meant by single agent but multi-user?
Multi-user কোথায়?
Two players but single agent.
Single agent, because the same agent is actually playing this, but from the perspective of two different players. Okay, you have one agent, but you are trying to simulate what you make a move when you make a move, like in a chess game. What you are moving, what is the opponent is moving. You are trying to simulate the perspective from both of them. That's why there are two players.
So the agent is playing from both sides.
Yeah, the agent is trying to play from both sides. He needs to see there's it cannot play if because you see in the adversarial search, what was the first condition? The first condition is if I make a move, the opponent is going to make a move again, and that move will be to undermine me. So if I only play from my perspective, I will never going to win. So if the AI agent only plays from his perspective, he'll never going to win. So to properly win, he also needs to understand what are the possible moves of the opponent. Just like we play a chess game, we don't just think what I can do. I also think if I make a move, what my opponent is going to make. You have to think about that way. That's how you actually play a game, and that is the same thing the AI agent is going to simulate here. Is it clear?
Yes, sir.
Acha. So let's try to understand the very simple tic-tac-toe game. Okay. That will be very easy to understand. This is the simplest one I could find. Acha. Some of the terminologies. Let's see. First of all, you have a state. Any state of the board, tic-tac-toe board, it is represented by S. Okay. Obviously, there is an initial state. Initial state is S naught. Okay. Now, in every state of the game, okay, let's say if we give a player function, it is going to tell you who is the next player. So let's say if I put an state here, assume x হচ্ছে ফার্স্ট, assume x makes the first move always on this game. আচ্ছা আচ্ছা in this condition of the board, who is the next player?
0. Cross.
X, the cross.
Cross. Okay, so try to focus from now on. It is based on you have to count. So if you write a like a AI algorithm, you have to make a count function. So how many x is there, how many o's are there? Assuming that x is making the first move, so 2 2, so the next is going to be x's. So the player function is going to give you who is the next move. Okay, so for any state of the board, that is the first thing you do. Determine who is the next player. Clear? Number 4, actions. Once you determine who is the next player, then actions is that all legal moves of that player. Okay, so once you determine who is the next player, the actions means what are the possible moves of the player. So for instance, in this board, how many possible moves are there?
5.
5. So if I write like this way, What do you do? Let's see if I give you this actions of this. What do you do? First, you determine who is the next player. Who is the next player?
Next player is 0.
Yes, 0 or O player. And what are the possible moves?
Possible moves 2.
হ্যাঁ, দুইটা, একটা হচ্ছে এইটা আর একটা হচ্ছে এইখানে, ঠিক আছে? So you go on like this way. First you determine who is the opposition player, then you find out what are the possible moves. আচ্ছা, number 5, results. Okay, results means if you make this move, what is the next new state? New state of the board. So results is represented like this way. Results of R of S comma A. Okay, it returns S prime. Taking action A on board S will result in the new state this. So for instance, for this scenario, if I make this move, the board becomes like this: X, 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 O, O, O. Since I made this move, this is the current value. Okay, so this is the result. Okay, for making this move, whatever the move, you can make actually one move at a time. So that is a possible move. And this is returned by the result function. Next, what you do, terminal. So you check if it is a terminal state. So whenever you check this result, whatever the new board state you get, you check whether it is a terminal state or not. Okay, so what does it mean? Terminal state means someone is winning or losing, or if the game is draw. Draw means no more moves. Okay, at the current state of the game, is it a terminal state? Is there any player winning at this one?
No,
Is there anyone losing?
no, sir.
No. Is there any
Draw.
more move available?
Yes. One move.
Yes. So is it a terminal state?
Yes.
No. If there
No.
are move available, then it is not a terminal state. Terminal state means the game, there is no more states available, no more moves available. Are you following?
Yes, sir.
So since there are moves available for the next player, so it is not a terminal state. So after you get the result, you check for the terminal state. So for instance, now, who is the next player?
Cross.
Cross. But we have already reached the terminal state, right? চলে আসছে না?
Yes, sir.
So terminal state is already true. So that means the game is towards the end now. So we don't have to go further. Okay. So see how we are doing. First, any board that you get, you find the next player, check the possible actions. Whatever action it takes, it will result in a new state. Then check whether it is a terminal state or not. So if it reaches a terminal state, that means the game is ending. So then what do you do? If there is a terminal state, utility. Acha. If terminal, only if terminal, you actually get the utility value. Okay, determine a score. The utility score. What is the utility score? Utility score can be either +1, 0, or -1 for the game of tic-tac-toe. Okay, so +1 means X wins, -1 means O wins, 0 means draw. Is it clear? So in this case,
Yes.
this is a terminal state. So in the terminal state, X means, so what is the utility score? +1.
One. +1.
So for this one, is it the terminal state? Is it the terminal state?
No, sir.
No. So should we calculate utility here?
No.
No, sir.
No. So we only calculate utility if the game reaches a terminal state. Okay. So terminologies are clear. Any question about these terminologies? 7 terminologies. Acha. So let's see. The algorithm, the MiniMax algorithm, tries to simulate all possible game states. So the algorithm, MiniMax algorithm, will try to simulate all possible game states that can take place. Acha. Until terminal. So terminal state means I am done. Okay, the algorithm is done until terminal state. Acha. The intuition is that one of the key intuition is that so the max player tries to maximize a score. That means it will always try to go to +1 or in this direction. The min player, so that is the X player, this is the own player, will try to minimize the score. It will always try to go -1 direction. Okay, so whatever the game board is, the max player always try to achieve this one. If it cannot achieve +1, it will try to go for 0, but it will always move this way. And the min player will always try to go in the opposite way. Okay, any question? Okay, so what is the utility of this one?
Not terminal state.
Yes, it is not a terminal state. So we are not going to calculate utility here. We cannot calculate the utility here. ঠিক আছে? আচ্ছা, let's see. Let me give a state of the game. X, 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 0, 0, 0. Okay, try to understand. So this is a state. Yes, given. What is the first thing we are going to do? We are going to find who is the next player. So who is the next player?
Oh.
O.
So the next player is going to be O. Okay. So the next stage is from the O player. We'll try to find what are the possible moves. How many possible moves can be there?
2.
2. So this is 1, this is 1. Let's see what are the possible moves. So দেখা যাক 1 2 3 4 1 2 3 1 2 3 4 1 2 3 আচ্ছা, one possible move. Okay, these are the possible steps. One possible move is here. That's the result. Another possible move is here. Two different scenario. Okay, are you following?
Yes, sir.
Yes, sir.
By making this move, we get this result state. By making this move, we get this state. So this is my S prime or S prime. Acha. Now, what is the next one? What do you do? কি ছিল মনে আছে?
টার্মিনাল স্টেটে আসছে কিনা ওটা দেখা।
Yes. Is it a terminal state?
No.
নো স্যার।
No. Terminal. Is it a terminal state?
নো স্যার।
No.
No, not yet.
So none of them is the terminal state. Okay. Then what do? You restart again. From this position of the board, you restart again. So since you have not reached the terminal state. So since it is not the terminal state, what do? New start. Now, who is the next player from this one? Who is the player now?
এক্স।
Cross.
X is the player. Okay. So what are the possible moves of the X player? X,
Only one.
X, 0, 0, 0, 0. So X has only one move, this one. Okay. Same thing true for here. X, 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 0, 0, 0, 0. If 0 had take this move. What is the possible move for x? This one. Are you following?
Yes, sir.
Yes, sir.
Answer. Now, if this is the game, so now what do? This is the resultant state. So from this position, what is the terminal? Is it the terminal state?
No.
No, sir.
Yes, sir. Yes.
Yes. Terminal state means
It is
win,
draw.
loss, or draw. No more
Draw.
move. There is no more move. So this is also a terminal state. Okay. For this terminal state, what is the utility score?
0.
0. So what is the terminal state for this one? What is the utility score?
+1.
Plus
+1.
1. Are you following? So think of it like this way. For this position of the board game, from this position of the board game, what is the move O player is going to make? Is it going to make this move? Remember কি করতেছিলাম? This was the position.
পাঁচটা দিব
Yes. This was the position of the board. From this position, O is the next player. We have to choose which move O is going to make. You see, if O makes this move, so AI agent is thinking, if O makes this move or this move, if it makes this move, the ultimate result is going to be 0. If the O player makes this move, the ultimate result is going to be +1. Now, from the perspective of the O player, which move is it going to make?
+1.
Left side.
Left side. Why? Always minimizing the score. একটু আগে লিখলাম না? O player will always try to minimize. So it cannot achieve -1. So what does it move? It try to achieve 0. So it will draw the game. জিততে না পারি কিন্তু ড্র করব, বাট হারা যাবে না। So it moves like this way. So from this position of the board, this is the decision O player is going to make. Are you following?
Yes, sir.
So do you get the idea how this adversarial search is working? From any move state of the game, you always think of what is the other player is going to make a move. You go until the utility you can find, then decide which move is the best one. Is it clear?
Yes, sir.
Yes,
Acha.
sir.
Let me give you another
Sir,
example.
Sir,
হ্যাঁ,
from perspective of O will also assume that X will make the best move for
yes, আমি
for
ওটা নিয়ে
him.
আসতেছি একটু পর ওটা নিয়েও বলতেছি।
Yes.
আচ্ছা, now let's try another example. If you have, like, if you are taking notes, try to play it by yourself as well. Try to do it by yourself as well. আচ্ছা, let's see. Okay. Okay. Now, in this, এটা কি একটু আগে খেললাম নাকি না? এটা খেলিনি, ঠিক আছে। আচ্ছা, in this position of the board, who is the next player?
X. X.
X is the next player. So how many possible moves does it have?
3.
3.
3 different moves. Okay. Let's see. So there will be 3 branch. That is the branching factor. বলছিলাম না branching factor, এটা হচ্ছে branching factor. 3টা ব্রাঞ্চ ক্রিয়েট হচ্ছে, 3 ব্রাঞ্চ। ওকে, সো 1 2 3 0 0 0, 1 2 3 0 0 0, 1 2 3 0 0 0। আচ্ছা, now from this position of the board, so X can either give this move, it can make this move, or it can make this move. 3 possible moves. ঠিক আছে আমার লেখা?
Yes, sir.
আচ্ছা, now, so from every one of them, what do? You check. আচ্ছা, so first of all, this is the resultant state. আচ্ছা, what do you check? You check the key condition, terminal condition. Is it the terminal condition?
No.
No. Is it the terminal condition?
Yes.
Yes. Is it the terminal condition? No.
No.
So from the terminal condition, what is the utility here? +1, right? X wins. ঠিক আছে? So X
Yes, sir.
win, this is the terminal state. And if X wins, you have utility of +1. So now what about here? This is not the terminal state, this is not the terminal state. So when it is not the terminal state, what do? You split again. You move on. From this one, who is the next player? O. From the perspective of the O player, now you play the game. You have X, 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 O, 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 X, 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 O, O, O. Now from this position, O will have two different moves, either here or here. ঠিক আছে? Now, again you check, is it the terminal state? No. Is it
No,
the
sir.
terminal state?
No, sir.
No. So neither of them the terminal state. So how do? You move on. Who is the next player?
X.
X is again the next player. So you play from the perspective of X. You see the branching the tree depth is increasing. Since you are playing adversary, so first you have the X player, then O player, then X player comes again. So now, if you play from the perspective of X, 1 2 3 4 1 2 3 4 এখানে বসো 1 2 3 4 1 2 3 4. Now X can make a move here, or from here X moves here. So again, you check the terminal. Is it the terminal state? Yes. This is the utility score of +1. Is it the terminal state? No.
Yes.
Utility score is sorry, yes. Yes, the utility score is 0. Are you following?
Yes, sir.
Acha. Similarly, if you follow this path, there will be two different paths. First, you have O player. For one, you will get utility score of 0. Another one, you will get utility score of -1. ঠিক আছে? তুমি ট্রাই করলে পেয়ে যাবা, কঠিন কিছু না। আচ্ছা, now see, so what do we have? From this position of the board game, from this position, we have total how many different utility? 5 different utility. Okay. If X makes this move, it wins directly. If X makes this move, ultimately it can win or it can make a draw, right? If X makes this move, it can draw or it might lose. Total 5 different utility. Are you following?
Yes, sir.
Acha. So obviously this is the obvious choice at this moment. +1. Obviously, if I make this move, I win directly. Acha. Think of it like this way. If let's say আমরা যদি বলি এভাবে, let's say I will not take this move, there is a good chance that I will win. The AI agent can think that he will win if he takes this move, right? There is a good chance that, let's say 50% chance he can also win in this move. So why not, let's say we'll try to go this way. আচ্ছা, এটা পসিবল কিনা?
Yes,
Yes,
sir.
sir.
Obviously possible. But you see, when you are designing the algorithm, you have to think another condition. What is the condition? The condition is you have to assume that the adversary is always going to play optimally. You always assume, the AI algorithm is always assume that the adversary, that means the opposition player, is always going to play optimally. This means that when I am saying that if I make this move, if I take this path, there is a chance that I can win. No, from the perspective of the AI agent, if you take this path, you will always going to do what? Draw. বোঝাচ্ছে আমার কথা?
Yes, sir.
Because the AI agent is going to play optimally. He is never going to choose this one. Because O player, from the perspective of the O player, it will always going to choose the best possible route. For him, the O player, the best possible route is go to 0. So from the perspective of this this one, this position, if X player chooses this path, the resultant is going to be, he is going to draw. আমার কথা বোঝা যাচ্ছে? Again, if you take this path, if the AI agent takes this path, there is a chance that he can draw. No, he is going to lose because opposition player is going to play optimally and the board is going to result in losing. Okay?
জি স্যার।
এগুলো লিখছে তুমি আমার করলে হবে? আমার কথা কি বোঝা গেল? বোঝো আগে। Any question? Any question? না বুঝলে বলো। So the game is being played in such a way, the algorithm is developed in such a way, the game is always going to be played optimally. That means when it comes to take a decision from the perspective of the X player, from all the paths, it has 5 different paths. One is the utility score is 1, 0, there is +1, there is 0 and -1 ultimately. Acha. So this is one factor, this is one path, one path, one path, one path. Acha. So you see, there is +1 and 0, but since it is branched already, branched means O player will have a move, so it is always going to play optimally. So the score, what you are going to get here is 0, never +1. You are going to get the worst possible scenario. Similarly for here, since it has been branched, O player has made a move, the best scenario that you are going to get is -1, never 0. So now it has 3 choices, either make this, this or this. So this is the only possible action. Okay. So if it plays this way, you can think that, okay, there is 50% chance, but from the perspective of the AI agent, when you design the algorithm, it has to be designed in thinking in mind that it is always going to draw if it goes this way. Is it clear? This is one of the core idea.
জি স্যার।
Acha. Let's assume that you have understand it. Now, see, this board game, like this tic-tac-toe, is a very simple game. But even here, there are around, I think, 255, 168. Here's a possible games. There are more than 250,000. Okay, 250,000 games possible. That means you see the trees that you are seeing. From this condition, there are, you have seen 1, 2, 3, 5, 6, 7, 8, 9, 10. If you start from this one, so from the first position, there are 8 possible, then 7, then 6. So the branching factor is significantly high. So there are many, many different ways the game can go. And the total number of ways is this. Achha. But it is still reasonable for a computer. This is still reasonable. Computer can still compute this kind of possible games. No problem. Achha. What is the problem is when the game is much more complicated. For instance, the game of chess. The possible number of pieces, chess pieces is 16 by 16, 32 places. So total 32 piece. 32 now? And
Yes, sir.
what is the total number of available space? কয়টা আছে? 1, 2, 3, 4, 3, 3, 6, 6,
Yes.
48 নাকি? যাই হোক, so there are so many moves that can be made in a chessboard. So the search area actually explodes, just explode. Okay, the tree branching factor is significantly large, huge. So the amount of possible moves is 10 to the power 120 plus. Okay, that's like incomprehensible from the perspective of human being, even from the perspective of the supercomputer that you have. Okay, it is so many possible moves that is, it is even greater. The number of possible moves in a game, chess game, is greater than the number of atoms in the universe. Okay, so that much complicated this game can be, the chess game can be. So there is no way a computer can actually simulate that many moves. Then what do you do? তাহলে কি করব? So in a tic-tac-toe game, I can go towards the utility, check if I make this move, what is the utility, and decide that this is the best route. But in chess game, you see there are so many moves that can be made. from the initial position to the last position, there are so many different paths the game can go. And there is no way any computer can actually compute that many path. Then what do? কি করা যায়?
Sir, there are many moves, there are many possible moves, but all of these are not logical. When we play chess, many of them
Yeah, there are not
is
all of
not
them are
logical
logical.
enough.
Yes, that's one thing. We'll go to there a little bit later. The first one that we are going to use a modified version of MiniMax that is called depth limited MiniMax. What does it do? So look up to 3 moves ahead. It is not going to reach the terminal state, but only take 3 moves ahead. Okay. So that means like you are considering only a predefined number. Without so when you are considering a predefined number of moves, you are not reaching the terminal state. You are not reaching the terminal state. For instance, if you think even from the tic-tac-toe, if you think from here, this is the first move with me. O can make 8 different moves. Do I simulate just from the first step that what are the different things that might happen if O makes this move? If I makes this move, what X is going to make a move? There are going to be 200,000 different combinations just from here. So there is no point of looking so far ahead because you see, game can go. If I make any of the moves, everything is going to be symmetric, right? তাই হচ্ছে না? So if X gives this first move, everything is going to be symmetric. If O makes this move or O makes this move, it is going to be basically the same. It depends more on what is the next move X makes. Then things starts to change. So you see, the idea is not to look significantly towards the end, but only 3 or 4 moves ahead. Especially for chess games, like complicated games like chess, it is completely impossible to look many moves ahead. So you only look at 3 or 4 moves ahead. আচ্ছা. Is it clear? The basic idea?
Yes, sir.
So that's why it is called depth limited. We are not going to go as much deeper because you see, even just from here, you have 1, 2, 3, 4, 5 deep, five branches has been created. আচ্ছা. Now, what is the problem that is created here? If I don't go to the terminal state, what is the problem there will be?
Sir, we cannot evaluate the move, whether
Yes.
it is good or better.
So if
Course.
we don't reach the terminal state, there is no utility score. We cannot get a utility score. Then what can we do? How can we evaluate the moves? So if we don't get the utility score, there is no way to evaluate different moves. So what do we do? What can we do is we create something that is called a evaluation function. Okay. So how do? We create a evaluation function. What is the evaluation function? A kind of a heuristic function. আচ্ছা. So this evaluation function is going to provide an estimated utility score. Not the exact utility, rather a estimated utility. Okay. So what kind of utility it can provide, estimated utility? That will be based on domain knowledge. Domain knowledge means depending on the search problem, it will differ. So for instance, if you're playing a game of chess, so if you're playing a game of chess, let's say from this position, you have 1, 2 move, 3 move, 4 moves, 5 different moves. Acha. Think of it like this way. Acha. And from here, there are 2 possible moves. Let's say just for Acha. The utility score by evaluation function will be created by some heuristic. Heuristics means, like for instance, if I make this move, is my chess piece get captured? বোঝার চেষ্টা করো. If I make this move, let's say one of the chess piece gets captured, then is it a good move or a bad move?
Bad move.
bad move. So you give some score, negative score. So it is the bad move. So let's say negative score, let's give -10. Acha. Now this is one heuristic. Then what kind of chess piece is given gets captured? If it is, let's say, a pawn, -10. If it is a knight, then let's say -100. If it is your queen, what do? Give it -500, because that's like you are almost losing the game. So based on what kind of chess pieces get captured, you define a numerical value. আমার কথা বোঝা যাচ্ছে? In tic-tac-toe, it was
Yes,
very
sir.
simple, +1 and -1. But now when it comes to evaluation function, you assign different values. So this is one criteria. There are other criteria. Let's say in another move. Okay. You capture a piece. So you capture a piece. Okay. So you capture a piece. What do? You give positive score. It can be +10, +50, +100, whatever the chess piece you are taking based on that one. Okay. So another move. Another move is like you get checked. So obviously, if you are getting checked, that's a very bad move. So what do? -1000. So it can also happen that none of this, like no piece is getting captured, nothing is captured. Then what do you do about the evaluation function? You use other heuristic, like what is your queen now? Is it closer to the opposition? Is it like in a good position, like position? You try to estimate the position. Then based on this, you create evaluation score. If queen is in a good position now, you give it +20. আমার কথা বোঝা যাচ্ছে? So
Yes, sir.
these are like different heuristics, just like you play a chess game, just like you think, depending on the the board space, the state the board is, you create a evaluation function depending on multiple heuristics, not just one heuristics. Then you add them together. Okay. So among this path, let's say this path has -100, this path has +20, this one is +1000, this is -200, this is -50, this is +200, +300. So among these things, all these things, which path you choose? This one. This one is the highest utility from the X player's perspective. Okay. Are you following?
Yes, sir.
Sir,
So from a
sir, are these scores will be accumulated over next 3 moves or just 1 move or 2 moves?
next 3 moves accumulated over. Okay. If you are looking 2 ahead or 3 moves ahead, you are continuously accumulating that if I make this path, if I take this path, this is the possible one that can happen. Okay.
Yes, sir.
Acha. So you look ahead, accumulated, like for instance, everyone will have their individual scenario evaluation. You make the final evaluation at the last stage. If you look 2 steps ahead, when you go to that stage, then you make the evaluation function. আচ্ছা, অত ভিতরে না গেলেও হবে, সমস্যা নেই। So based on all this possible, you take the move. Okay, best scores. That's how your evaluation function is actually working in this way. So is it clear how depth limited search, minimax search actually calculate the estimated utility and get to a decision function? Any question?
Yes, sir.
আচ্ছা. So you have your depth limited search from a position. You can have multiple moves. Every move will have some score value, and based on that you choose. So if it is the max player, what will the value this one is going to choose?
9.
9, obviously. আচ্ছা, ঠিক আছে. Now, is this 100% accurate?
No, sir.
No. What is the probability that it is accurate? You can actually think of it like this way, that there is no way to completely accurate, because search space is so big, there is no way to 100% completely accurate it, make it perfect. Unlike your tic-tac-toe, this is simple, but when it have such complex search space, there is no way to make it 100% perfect. So you try to optimize it in some way. So when you try to use this kind of heuristics, any heuristics, there will be some drawbacks, or what do you say? এটাকে বলা হয় pitfall. আচ্ছা. One of the pitfall that happens from this one is called the horizon effect. Okay. So what is the horizon effect? That is, let's say if you fix it as 3 move in the depth limited search, if you fix it at 3 move, you cannot see past 3 moves. That's the maximum one you can see. So the utility, the scores that we're getting, it is not perfect, and some bad things might happen. What kind of bad things might happen? Let's say you make a move, you chess piece caught. Okay. You use your queen to get opposition's, let's say, pawn. Okay, in 3 moves. In 3 moves, you get from your queen, you get the pawn. So since you captured a pawn, you get a plus 10 value. So ultimately your score is very good. It is the best moves and you have made it. Fine. Okay, you are happy with it, you have taken it. But you see, in the 4th move, it can happen because you captured up to 3. In the 4th move, it can happen. The queen is now captured. The queen is now captured by opposition's rook. হইতে পারে না?
Yes, sir.
So if you know the game of chess, it will become very easy to understand. If you don't know, definitely go and learn chess, because for this lecture, just for this one, you have to understand chess. Acha. So it can happen that in the 4th move, you have taken one piece, but in the 4th move, queen is getting captured in rook. So is it a good move then? Because you are losing queen just
No,
for
sir.
a pawn. So definitely a very bad move. But you cannot see that because you have stopped your search at what? In 3rd move. Are you following?
Yes, sir.
You see, this is called the horizon effect because you cannot see beyond that depth. Okay, that's the horizon. You cannot see beyond that depth. That's why it is called the horizon effect. And this can actually drastically reduce performance, okay, of your chess, AI chess board, your AI agent. It can perform very poorly because of this one. Okay. So what do? We need a solution, right? Performance significantly worse it can. So we need to get out of this problem. Okay. So how can we get out of this problem? The solution to this one is called Quiscence search. Okay. The solution of this one is called Quiscence search. Acha. So what this one does, it avoids evaluating unstable positions. Okay. At card depth. So you see, in a chess game, you can have 100 different possible moves. And there are many moves, they are just very simple. You can easily ignore that. There are many moves you can simply ignore. So that's not a problem. But there are moves that you should not avoid. For instance, in this case, your queen is taking a pawn piece. So even if you are at the card depth, but still, if you want to choose it, you have to make sure that in the next move, your queen is not going to be captured by the opposition. Okay, so when queen is capturing this pawn, that is an unstable position. Are you following? So what do you do? হ্যাঁ বলো।
Sir, here card depth means
মানে কাট ডেপথ মানে হচ্ছে যে 3, যেখানে আমি ডেপথ লিমিটেডটা শেষ করতেছি। So if the positioning is unstable, you carry on. You don't stop, carry on. That means you don't calculate the evaluation score then. But what do? You calculate, but you carry on. Carry on to check until your position, your piece is at a stable position. So after the chess, let's say the queen makes this move, you go to state 4 and check, is there any way my queen can be captured by the opposition? If it is not, then you stop. You stop at 4. বোঝা যাচ্ছে আমার কথা? So there has to be some heuristics. There is obviously some heuristics to identify the unstable positions. So when you find, based on that heuristic, when you find your T space in a unstable position, you carry on your search algorithm until you reach a stable position. Okay. The basic idea is there should be no hanging piece. No hanging piece. Okay. That means undefended piece. Is it clear?
Yes, sir.
So you carry on a search a few more steps ahead. It might be 1, 2, 3, even 3. You keep on, the Quiscence search will carry on until it finds a stable position. Okay. So the search depth for that particular scenario increases. Not for all, but for particular piece, particular position, that one. Okay. So when you do that, the stability of the game increases, the strength increases. Okay. Previously, you saw in depth limited search, the algorithms actually lose performance significantly because due to this kind of horizon effect. So when you ensure that your chess pieces are in a stable position, then you stop the search. So the strength of the AI agent significantly increases. Okay. Acha. But what can be the drawbacks of this one? What can be the problem with this one? This will take more time, right?
Yes, sir.
More computation power because you are watching past that depth. So obviously it is going to take more time and more computation power. And one thing can happen, that is again pitfall. So that's like you are going, but you are not reaching a stable position. You are checking 4, 5, 6 depth, but you are still not finding yourself in a stable position. Then what do you do? বোঝা যাচ্ছে আমার কথা কি বললাম? You normally
Yes,
cut
sir.
at 3, but since the position is unstable, you keep checking. Fourth position, it is still unstable. Fifth, unstable. Sixth, third step is still unstable. Then what do you do? You carry on. If you carry on, it is going to be a very large search space. So what do? You let go. You let go of the path. You don't need to take a risky move rather than stay on a stable move. আমার কথা বোঝা গেছে? That will usually give you a better game fight. Is it clear? Any question? Any question? আচ্ছা.
So, sir, we have to define depth, maximum depth. So, like
Yeah.
5 or 6. After that, it will let
Yeah.
the move
5
go.
or 6 না মানে হচ্ছে how many moves ahead from the depth limited minimax. If it is unstable position, how many moves I can go on before I stop searching. Okay.
Yes, sir. Understood, sir.
Acha. So we have seen the minimax algorithm. Then we have seen the depth limited minimax algorithm. Then we says even better than that one is the Quiscence search. Then the last version of this one that we're going to see is called alpha beta pruning. Okay. This one একটু বুঝতে হবে. This one actually makes the efficiency of the game, increases the efficiency of the game significantly. Pruning means you are going to prune certain moves. Pruning means you are going to prune certain moves. What kind of moves? Achha, we'll see. There are different moves that we need not consider that happens in a search, very large search space. So just simple redundant calculation. Okay. So you can have some intelligent way, intelligently remove redundant calculations by just avoiding bad moves. Without even calculating those things, you can say that this is a bad move. Okay. Without even calculating those search area, you can just say this is a bad move and you can just prune those moves. Okay. Acha. So how does it work? To do this, okay, you keep track of the best scores of your max player or maximizer and minimizer or min player. So max players is called the alpha, mini player is called the beta. That's why it is alpha beta pruning. Acha. Acha. Now remember what is the game. The max player will always choose the best score, min player will always choose the lowest score, right? Acha. Let me now give you a problem. Try to understand. Acha. Let's say here at A, this is the max player position. Okay. Max player has three different routes. B, C, D. Okay. So BCD, this is the mean player's perspective. From the mean player's perspective, there are three routes. There are three routes. There are three routes. Okay. And then you have the evaluation score. This is the expected utility. Understand? This is like adversarial search. First max player, then min player, then Acha. So from here, so max player is going to make the decision. Okay. But it is taking from the perspective of the mean player. Acha. Now, from the perspective of the mean player, among 4, 8, 5, which one is going to be chosen by a mean player at B?
4.
4. Fine. Acha. Now, in this path, the first one you get 9. Okay. The second utility score you get 3. Okay. Now, do we calculate the next one?
No, sir.
Why not?
Because, sir, the mean player will obviously choose 3.
Acha. What if it is less than 3?
Sir, we have 4, which is greater than 3, or whatever he chooses.
Acha. So here you can see in this position, two things can happen. It can be greater than 3. Okay. Acha. Let's assume the score is either, let's say, 10. If it is 10, is C is going to choose what? 3. It is not going to choose this one because this is a mean player. Let's say if it is 1, what C is going to choose?
1.
1. So whatever the value is, it is always going to be less than 3, right? Less than or equals to 3. আমরা তো এটা বলতে পারি, তাই না?
Yes, sir.
So
Yes,
why
sir.
does it matter? It matters, you see, the ultimate decision is going to be taken by the max player. From the perspective of the max player, you already have 4. So whether it is 3 or less than 3, it is never going to choose this path because it already has something better here. Are you following?
Yes, sir.
Yes, sir.
So from the perspective of the max player, you already have something better. So you are never going to choose that path. Now from the D, let's say you have 2 here. Do I check the utility score of the other moves?
No, sir.
No, I will not go this, I will not check this. আমার কোনো দরকার নেই because this is going to be less than equals to 2. And since it is less than 4, it is never going to choose this path. So it is always going to be 4. Is it clear? আমার কথা বোঝা গেছে?
Yes, sir.
So what you are
Yes,
doing
sir.
here, from the perspective, you are pruning different paths. And when you have a very large space, 2000 different moves, you can actually prune 1500 of them just by this way. That's why I said, when you apply this alpha beta pruning, the efficiency increases significantly. Performance boost. Okay, because there are different moves. You can think from the chess pieces perspective that there are different moves you don't even want to know. Okay, that this move is not going to give you anything. So there are far better moves ahead. So let me. Okay, this is the last one. First you have A, B, and C, then D and E, F and G. Okay, so this is your max player, this is your min player, this is your max player. Then you have two here, two here, two here, two here. So this is 3 and 5. Acha. Now, so what is D is going to get?
5.
5, because this is the max player now. Acha. Here you get 6. So do you check the next one?
No.
We don't check the next one because this is the max player. It is obviously going to be greater than 6, right? And
Yes, sir.
the reason we are not going to check further because fair from the perspective of the mean player, it is always going to be 5. It is never going to be 6 or higher. Clear? Acha. Now come to the F. The first one is 1, the second one is 2. What is F is going to get? Obviously 2.
2.
Then do you check G? Do you check any of the
Yes,
G?
sir.
Yes, sir.
No, we don't check. Because from the perspective of the mean player, it is always going to be 2 or less than 2. Whatever the value is, it is going to be 2 because the mean player is going to choose 2 or something lower than that. And from the perspective of the max player, it is always going to choose 5. It is never going to go 2. আমার কথা বোঝা যাচ্ছে?
Sir, what if G has 0?
Fine. 0, if it is as 0, this is 0, this is 0, still it is going to be 5. See, there are 3 branch here. In the previous example, there was only 2 branch. Now you have a larger one. So the max player, let's say 0 is the best one. So it is going to choose 0. This is going to be 0 because it's the mean player. Then the max player is going to choose 5. Okay. Is it clear or still not understood? একবার চিন্তা করিও. It
Sir,
will be clear. বলো.
sir, if G has 0, then minimum, then C should choose, then the min player should choose 0, right? Because all other points are greater than 0.
So let's see. If mean player এখানে 0 আসলো. Okay. So let's say the GS gets in 0. The max player from the perspective of the max player, this is 0, this is let's say -2. So the max player is going to choose 0. The mean player is going to choose what? From 2 and 0, it is going to choose what? 0.
Yes,
Now,
sir.
the decision making is from max player's perspective. So max player is going to choose 0 or 5?
5.
5. So is there any point in calculating these things? No.
No, sir.
Again, আবার ধরো এটা হচ্ছে 2 না, এটা হচ্ছে 10. If it is 10, what is going to the max player choose? 10. So among 2 and 10, what is the mean player is going to choose? 2.
No.
So again from 5 and 2, which one this max player is going to choose?
5.
5. Okay. So this is the way the search guys goes. You actually prune any unnecessary. You just have to write a simple code just to check, and you prune based on that one. Okay. And this makes your algorithm much more efficient. Okay, significantly efficient. Acha. Any more question?
Sir, for this algorithm, we should also have some depth limitation, like up to 50 or 100 times.
Depth means depth, we never go to 50 depth. Depth can be maximum 5 or 6 usually. Search space becomes very large by that. Okay.
So
Yes,
that
it
means
is
for
after
alpha
depth
beta
limited.
pruning is also we have a limitation of depth for search
Yes, of
space.
course. They come serially. You see from the way I first said. First you have MiniMax, then you have depth limited MiniMax, then you have Quiscence search, then you have this alpha beta pruning. Okay. This is like the better version you have seen, the best version so far. Okay.
Yes, sir.
Any other question?
Sir, is it necessary that the move will always start from the max player's perspective?
No. Whoever places first, that's the max player. Fine. No problem. Alternative.
So then the calculation will be opposite in that case.
Opposite. No problem.
Yes, sir. So the starting player matters here.
Yeah, the starting move preference. So if you are a white player or black player, that changes everything. Okay, but ultimately, from the perspective of the AI agent, they are both the same thing because it is going to simulate both. Okay. Any other question? Okay, write your student ID in the chat.